Welcome back, everyone. Now we get to see how the field tensor is actually used in a field example. And in this particular context, what we want to do is for a straight wire along the z-axis, which carries a charge density lambda, traveling in the positive z direction at speed v, construct the field tensor and the dual tensor at the point x, 0, 0. All right? So, we just dealt with a wire question not too long ago. I think it was 44. But now we get to see it again, and this term we get to put it into a field tensor. And we have to realize that the field tensor is composed of two parts. The F part, which gives us one half of the equations, and then the dual tensor, which we have to use these substitutions on the right-hand side to find, gives us the other two equations for Maxwell's equations. That being said, the tensor is constructed here where our main diagonal is 0, and we have the components x, y, z negative, again, spatial directions here. So be aware of that for when the temporal domain is 0. And then for all these spatial transformations, we have combination of bx, by, bz. Again, the anti-symmetric nature of it means that we have negative signs when we fold over across the main diagonal. And then, of course, the dual tensor, once we complete this quick little transformations, then we see we have the other set of equations. So, let's see. For this to start off with, what we need to know is the electric and magnetic fields of the wire. So here, we know from other methods back in chapter 2 and 3, what this would be via Gauss's law. Here, what we want to do is go ahead and set ourselves up in an advantageous position, meaning that we want to put everything in the same kind of base units here. Notice that we would have had in other examples, we would have had lambda over 2 pi epsilon naught with the hat direction over the magnitude. Here, we're going 1 over 4 pi epsilon naught and putting the 2 lambda up top with the x. Why are we doing this? Well, we can cancel the 2, cancel the 4. That gives us 2 pi. But what we really want to do is put everything in terms of mu and c squared. So that being said, we have a mu over 2 pi, lambda c squared x. The magnetic field, of course, is equal to mu naught over 4 pi, 2 lambda v x, because again, we took the cross product of the E with the V. We found that through pretty quick there, I would say. Nonetheless, they cancel down, and we see that we have mu over 2 pi in both of them, a lambda over x in both of them, and a c squared for the E and a v for the y, a v for the B. So again, try to make them as symmetric as possible for when the dual subs have to happen. That being said, we see that this only happens in the x direction, so when we plug this in here to the Ex over c term for the field vector or the electromagnetic field tensor, we get a lot of cancellation with c's here, so we like that, easy enough. 0 over c for the x or for the y and z components, we like that. Notice that the bx and bz components are canceled to 0 as well, and we just put the negatives in for the y components. That being said, we can tidy this up really quickly, and so quickly, in fact, that we could factor out a common factor of mu naught over 2 pi lambda x. And this is where having them written in similar forms up here was able to condense this tensor down into something really easy, respectively, to deal with. That being said, we still have to find the dual tensor. So similarly, to find the dual tensor, we just do the substitution to get us from F to G. Again, so that puts all the bx up top, all the bx here, and then the combinations of E over C where the bx, y, and z used to be. That being said, we still have the same foundations. Put in zeros where we need to, and then we'll just simplify down and factor out like we did last time. So you see here that when we apply the dual transform or the dual tensor, we still get the v and c's respectively, plus or minus, of course. But we still get this mu naught over 2 pi lambda over x out. So this is just how we set up the field tensors. Again, in order to recover the four Maxwell's equations, we have to have the F field tensor and the dual tensor. And those two together give us all the equations. That being said, if you notice that the dual tensor and the magnetic field tensor, one of them gives us the current density 4 vector, the other one gives us the zeros. Those are for the divergence and curls, things of that nature. A lot of write-up on this stuff because it's fascinating, but these tensors are what we're going to use in a lot of theory moving forward. So very, very important to get used to this, and very important to get used to the notation. We'll see this in more action here soon, so this won't be the end of it. But until next time.